Boleh nampak semua ke? Please respond to chat box ataupun verbally. Okay, very good. Okay, nampak. Okay, so this individually, seperti yang saya mention last class, sometimes taking sample in terms of subgroup, okay, it is costly. And also because of automation, we are able to individually measure the individual product that we produce. It can be any products that going through the process. It could be metal pieces, it could be rubber pieces, wood component, or any component that coming out from the machine. Okay, we can individually measure through automation. We have vision system, we have sensors. Okay, in the past, you have to take out this component and measure it offline. But now, due to automation, we are able to measure individual pieces. So this is becoming more important now, measuring individual values rather than the average of n, which is subgroup sizes. Because normally n, I mentioned earlier in X bar chart, we can take, for example, n equal to 4 or 5. Okay, but now because of automation, we can measure individually, which is n equal to 1. So the issue now is we have in control charting, short control chart, especially on X bar chart, we assume that the data is, we call it independently, it is independent. It is not correlated. It's independent value, independent and normally distributed. So what happened is there is issues when we are taking individual data. Individual data not always following normal distribution. Not always follow normal distribution. Okay, so the issue now is tendency that it will be deviate from normal distribution. Okay, I put it in this slide. How we can check normality? We can check normality. Okay, for example, using this normal probability plot. Normal probability, we can put this in Minitab. Minitab is one of the popular statistical package that you can use for control chart as well. Minitab, for example. So we can have, if we have a straight line like this, if we have a straight line, see here you have a straight line like this, and most of the points are plotted within this line, okay, very close to the line, okay. Of course, there will be a measure on that. So by using our eyes to inspect this, okay, we see that most of the points are very close to the straight line. Okay, this is based on normal probability plot. So based on this, what we call it crude estimate, okay, we can see that these are coming from normal distribution. So this is shown in your example that we have discussed earlier related to see the variability of mortgage loan application, okay, that we have plotted here in this example where the data is given in this table. Okay, the data is given where we have weeks. Okay, we have data in terms of weeks. We have in terms of cost. Okay, we want to see, okay, the cost of processing mortgage, how it varies. Okay, how it varies. So week 1, this is the cost. Okay, week 2, this is the cost. So is there any unnatural variation happening here? But remember, this is individual data. Because of it has individual data, we always want to have it the mean and also the range. Okay, but in this range, okay, range is measuring the dispersion. Dispersion. Okay, I always show this normal distribution. So the mean is we are targeting here, or the center, the target. This is the setting. But the range or the standard deviation between this line and this line. Okay, so this is showing how it varies, the dispersion or deviation from the mean. okay, deviation from the center line. So this is shown in terms of R. Normally it's R because R is showing maximum minus minimum. Okay, this is the simplest way to show the range lah. Okay, you get the maximum value here, minimum value is here. Because we are taking individual here, so what we do is we take MR, okay, moving range. Okay, moving range. I already explained this before. So the moving range. So it's showing this. So we always in monitoring process, we always look at the center, how the center, okay, the position of center, and also how it is related to the range. That's why we always have X bar and R chart. We always have chart that we have earlier chart that we have seen that X bar always coupled with R chart. Here we also have X bar and S because the X bar is showing the center, R and S is showing the dispersion. And now we have X chart, which is individually coupled with MR, which is moving range. Okay, R showing the center and R is showing the dispersion, which is showing how it's dispersed. So as far as possible, we wanted a small dispersion. It be on target, but it is slightly meaning that the variation is not so far from the center. That is the best process. All right, so in this X bar and MR chart, okay, because it's individual, we know that individual value is very sensitive to the distribution. It can deviate from a normal distribution. Okay, so earlier also I already mentioned about the how can we eliminate non-normality. Okay, for example, using central limit theorem. Okay, central limit theorem. You must understand this. Central limit theorem, where the distribution of individual value may come from non-normal distribution. It can be coming from, okay, let's say, maybe a process which is, let's say, the distribution is coming from a uniform distribution. Okay, like for example, you are throwing your dice. Okay, the dice have 6 heads. So the chances for each head is equal if we have a die which is a perfect cube. 1, 2, 3, 4, 5, 6. So this is going to have 1/6 chances for every face of the die if you toss this die. So okay, so what happened is in control chart, okay, we would like to have a normal distribution as close as possible. But if you're plotting this, for example, you get a normal uniform distribution, you may have even triangular distribution. Okay, you even may have, okay, I mean in general, not limiting to the dies. You may have distribution which are perhaps maybe what exponential distribution, okay, negative exponential, and so on. So central limit theorem says that if we take the averages of the individual value, okay, if we take the averages, the distribution of averages tend to be normal distribution. That's why we take averages. But now the challenge is what happened in automation where most of the inspection is done individually. Okay? Yes, you still can have normal distribution, but before we proceed with control chart on this individual, okay, we have to be cautious. Kita kena berhati-hati. We have to be very cautious on this. Okay, so in this slide, it shows that okay, okay, we can check whether it's normally distributed or not by using normal probability plot. Okay, if it's normal distribution, and then there is no issue of using control chart, short control chart. Okay, let's see in this example 6.6, where we if the distribution is not normal, we can transform this. So we call it using the transformation. Use of transformation. Okay, we transform the data from raw data. In this case, we have 25. We have 25. You have here sample. Okay, you have sample here. Resistivity is just a measure of a parameter. Okay, in this case is a measurement of resistivity of 25 silicon wafer. Okay, so a wafer in the electronics, so they are measuring the value of resistivity. Okay, so and then okay, of a single wafer deposition process. So individually measure. Sample one, okay, 1 unit got 216. Okay, the measurement. Sample 2 got 290, and so on. Okay, until the sample we have again sample here we have until 13 on this side, also continuing 13, 14 until 25. Typically in control chart, as I mentioned earlier, we need okay 20 to 30. 25 is normal practice because easy to calculate 25. So you have 5, 5, 5, and then you get. I mean, in this case, it's not 5. It's n equal to 1. So it's measured, and then okay, you see here in this column. Okay, in this column, what we have here is we have ln in the natural log of x of this value. Okay, and mr. Mr is the okay, the difference between R2 and R1. Okay, so instead of using raw data, we take it natural log of x of this measure. So we get 5.3. Okay, and we get 5.66. So now it's being transformed into natural log value. Okay, so with that, you see, if we plot the individual value, if this is the plot of the resistivity original value, okay, original value, see the original value, we have the original value here, okay, ranging from, all these values, where is there are 1339, there are 240, 447, and so on. But when we put in the logs, it's a log value. So this is what is showing here. Normal probability plot of ln, okay, of resistivity. So you see that here it is look like closer to normal probability. Okay, normal probability compared to this one. You see this one. Okay, we have values that are deviate from the line. The closer to the line is the better. So when we plot on the chart, okay, if you see the chart here, individual, what we plot is the transform value, ln value. So you see that this is the values these are moving. Okay. So, and this is the MR. Okay. So we also have to be careful with MR because we are taking the individual values next to each other. Okay. If you see here, this value here. Okay. If we check through the runs rule, okay, we can see this. Okay. This value is supposed to be okay, up and down, not like this one. This is down, up, down, down, go up. Okay, and then this one is down, down, down. So the independent values, the independency of the values is not as good as when we take the X bar values. Okay, so we need to be careful on this. So in this slide, it is shown here that okay, on the figure 622, okay, figure 622, which is this figure. Okay, this figure. Well, it says that okay, not the best. Okay, it is clear that from inspection, okay, from the inspection of the normal probability plot, okay, that normality assumption for sensitivity is at best questionable. Okay, it's questionable. It would be dangerous to apply an individual control chart to original process data. Okay, because this is a process. This data is original data. Okay, original data. That's sensitivity. So that's why, okay, we take this the natural log of the original data instead of using the raw data. Okay, so figure 623 indicate that distribution sensitivity has a long tail to the right. Okay, consequently, we would expect log transformation or any other transformation to produce a distribution closer to normal. Okay, so long tail, has a long tail to the right. Okay, you see here. Okay, so it ran away from the line. So it is recommended to make transformation. This case. Okay, so okay, normal probability plot of natural log of resistivity is shown in figure 623. So this is what is showing here. Okay, this is natural log of this. So you can see that here, the difference here. Okay, this is far away, right? So this is getting closer. Okay, these 2 points. So now get close to that. Okay, this 3 point. Okay, 3 point now, very close. And also we can, maybe if we don't look carefully, it looks the same, but actually it's not. Huh? See, this one is very far away, and now it's getting close to here. Okay, so meaning that when we transform, the data is closer to normal distribution. Okay, so it is recommended we transform the raw data to natural log. Okay, so the log transformation has resulted in a new variable that is more nearly approximate by normal distribution. Then the original resistance measurement. Okay, so we need to be careful. This is my point here, is we need to be careful when we take individual values, because now automation becoming more common. So unlike in the past, people are taking data from manual activities, so you are able to take the averages, values, and so on. Okay, so most likely you will be dealing with individual data. So be careful. If the individual data, we may need to transform this into log or natural log before we plot data. Okay, the last column on table 6.8 show moving range of natural log of sensitivity. Okay, so when we take the log and this data, they also have to take from the log. So this is moving rate of the natural log of n. Okay, which is this value is the difference between 5.66. Okay, 5.66. Okay, 66988 minus 5.37, you get this value. Okay, the second one, take this and you get this one. Okay, this is what we call it moving range. Okay, moving range. Okay, any questions so far? Is it okay? All right, very good. Okay, Zohair, thank you. Okay, okay, when we estimate, that is also another challenge for us is to estimate the value of sigma. So we can estimate the average, the value of this sigma. We use, okay, in practice, we use moving range, okay, in estimating the sigma. Okay, sigma value is the dispersion value of the process, yes, or process standard deviation. So in moving range, okay, it's defined as the difference between, we know already, the current value minus the previous value to get the moving range. Okay, so this is what is showing here. MR moving range for the sample number I equal to xi minus 1, meaning that the present value minus the previus value. Nanti the M, M is the number of data that you have. Okay, so this statistic should be called a moving range of span 2. Okay, so most common estimator is the one we use in example 6.5, okay, that we have seen earlier, based on moving range. Okay, so moving range is given by average of moving range given by this formula, summation of MR divided by n minus 1. Okay, so this is straightforward lah. Okay, if you want to get this value of moving range, we add all these values. Okay, add all these values. Okay, 25 minus 1, because why? The first one, there is no values. Okay, on the first one here, there is no values. So meaning that we only have 24 data. There is no values here. Okay, that's why you have M minus 1. Okay, this is what the formula is showing here, the moving range. And can be also written as, okay, so this is can be simplified using this formula. Okay, if you want to estimate, okay, sigma for the process, okay, where the constant 0.8865 is reciprocal of D2 for a sample of size, okay, n equal to 2. Remember that D2 is coming from the table. Okay, so these values 0.8865 is 1 over D2. Okay, for a control process. For in control process, okay, this author, Ryan and Rand, okay, among others, have pointed out that a more efficient estimate is one based on sample standard deviation. So we can also estimate this, okay, this sigma estimate, okay, from S divided by C4. Okay, so different way of estimate the process standard deviation. Okay, so both estimate are unbiased, assuming no assignable costs are present in the sequence of n. So you can use this way or this way to estimate the sigma for the process. Okay, sigma of the process. All right, in this slide also shows that when we have, these are summary of formulas lah, okay, summary of the formula. So when we are given a standard, given, normally this is, we get it after revise lah, after revise, after we revise. Remember that we have phase 1 and phase 2 control chart. When we revise the control chart, okay, for X bar chart, okay, so the mean, okay, the mu here, okay, mu of the process lah, but sometimes we estimate this mu from X double bar new, where we remove unstable data which are related to assignable cost, so we call it X. Sometimes this symbol also used as X bar node. Okay, but we assume that it's a standard value, okay, standard value. So different notation is being used by different people. Sometimes they use like this to show that the standard value, which is sometimes also estimated from the new. The new here, okay, is actually coming from, okay, you have the X summation of X double bar minus x bar discarded value, di mana kita buang that value because it's assignable cost. So when you have, for example, G here, okay, or in this case they use M, it doesn't matter which one. So how many values that you remove there, okay? So once we have this phase 2, the standard value, okay, or after the revise, so basically this is for phase 2, phase 2 in the control charting, where we remove unstable data due to assignable cost, we can use this formula, okay? Okay, x plus minus a sigma 2. Previously, it was like this. In this is basically, we say that it's no standard given. This is basically a trial control chart. Or we can say this phase 1. Okay, in phase 1. The phase 1, phase 1. The phase 1. So we use A2, but when we revise, we use this value. Okay, same also for S chart, X bar and S. So the trial, we use A3. But in this case, the S1, okay, we can use this one as well, okay, when it is given. But for the X, the trial one, A3, A3 S bar, okay. Sorry, X double bar plus minus A3S. So if we are using this, this is on trial X bar S chart. This is trial X bar R chart. Okay, so this is common, the trial one. We also know this D3, D4, and this for S, the trial for S, these are the formula. But when we revise, it's going to be B6, B5, and B6. Okay, so this is just giving you the summary of that formula. All right, any question to that point? Okay, let me move on to okay, we have discussed on this EWMA. Let me continue on the EWMA. Okay. So this EWMA is on chapter on chapter 9, chapter 9. Okay, if you see on chapter 9, we have cumulative sum. Okay, have you seen is it appear on your screen? Yeah, so let me just confirm with you. Yeah, okay. You see now, right? Okay. So this one is cumulative sum and exponential. So these are two common control chart that is used. Okay, it can be used for individual values. Okay, and also can be used for the mean values with the averages values. Okay, so let me go to this page 413. Okay, last before the break, we already start discussing this the exponential values. Okay, exponentially weighted moving average, exponential moving average, and this method actually also can be used for forecasting. Okay, if we study um, forecasting, this method EWMA also quite effective in forecasting. Okay, so cumulative sum is in short form, we call it CUSUM. Okay, cumulative sum is CUSUM. Exponentially weighted moving average is, we call it exponentially weighted moving average. Okay, we call it EWMA. Okay, MA is mean moving average. Okay, moving average. So okay, let's start with this. Okay, we have start discussing on this CUSUM. CUSUM control chart for monitoring process mean. Okay, we are monitoring the mean of the process. So meaning that if we have normal distribution there, we are trying to monitor this mean. Okay, how this mean varies. Okay, how the mean is varies. Okay, so in this data table 9.1, okay, what we have is 20 observation. Okay, so which are taken from a normal distribution with a mean equal to mean of the process. Mean of the process is given here equal to 10, and standard deviation of the process is given as 1. Okay, as 1. Okay, the center line. Okay, the center line. See here, this is center line. Okay, it's 10. Our target is 10. Target 10. This is where we plot. We plot this on short control chart. Okay, of this data. This data that we have here. Okay. Remember, this is individual values. Individual values. So you have until 30 values. Okay. So we plot it on short control chart, the regular control chart, which is in this case is X chart. So what we see here, okay, we don't see any shift. There is no shift visible unless we carefully look into it. If you see now the point, if we apply run through, we may already detect something here because it's moving up, up, and up. Okay, so it go down and down, up again. Okay, naturally it should be up, down, you know. Okay, like this still okay, but okay, you have up, down, down, and then up again. But in general, we see that it's in control. Okay, but here we see there is a shift, slightly a shift here. Okay, slightly shift there. But if we apply the runs through number 1, so we may end up with conclusion that the process is in control. Okay, the process in control. It looks like in control. It doesn't look very obvious by looking by our eyes. By our eyes, it's just saying that it's within control limit. But when we plot this, okay, using cumulative sum, okay, this is cumulative sum. We plot the same data on cumulative sum. Okay, so what we get is very clear that after this point, the process is running away. Okay, anyway, so this is very important when we select what type of chart to be used. X chart cannot detect this, but CUSUM is able to detect this. Okay, CUSUM, cumulative sum, able to detect this. Okay, so we take action before it's getting more defects. Okay, because defects after the process is waste. Okay, we are losing. So if we can detect it earlier, but if we kept continuing using X bar chart, you see that we assume that, oh, everything is okay, no problem, because it's within control limit. I hope you get this understanding. Is it okay? Can you respond? Are you clear on this? Okay, please respond to your chat, to the chat. Okay. So I get a response there. You say okay, right? Okay. Okay, so that's why we need to use a proper and more sensitive control chart. Okay, so one way is using this CUSUM, cumulative sum. So you see here in this um, method of CUSUM, we have xi minus 10. 10 is our target, the mean that we know that the process mean is 10. We need to know what is the process target in order to use CUSUM. So now we have 9.45, okay, minus 10. So we got the difference is minus 0.55. We keep continuing doing this, so we get the minus, positive, and so on. And then in order to get the CI, this is the cumulative. This is just only the difference. This one is the difference, the difference of the values. But in order to get the cumulative, this is the cumulative values. CI equal to xi minus 10, which is coming from column number 2, plus CI minus 1, which is the previous values. Okay, so this formula is where you get the cumulative, meaning that the previous value play a role in our monitoring, not only the last point. So the difference between previous control chart, which is short base, is only concerned about the last point, but this case is cumulative point. Okay, so like you have CGPA and GPA. Your CGPA is cumulative. Okay, if you score poorly in earlier semesters, it affects your current CGPA because it's cumulative. But if you just follow GPA, you don't care whatever whether you are scoring poorly or not so good previously. It will not affect your current GPA. But if you look at CGPA, okay, previously poor performance will be affecting your current CGPA. So the same thing here, cumulative. Okay, cumulative. So what we have here is the first C1 is the same, but when we get the C2, so this C2 we have minus 2.01. Okay, again you have the previous line which is plus here, the plus C2 minus 1, which is C1, which is minus 0. Okay, you have 0. Okay, because this is plus, plus, and you have minus, so it will become minus. Okay, 5. So with that, you're going to get minus 2.56. Okay, the same method continue. And the next one, you have 0.71. Okay, minus the previous one. Okay, the previous one, okay, the previous one was this one. Okay, so which is 2.56. Okay, you get this value. So keep continuing doing that, okay, until you finish all, until the end. You see here, what you notice here, when the point is shifting, you start to notice here. Okay, this value keep increasing until you have it here. So this is what is being shown in this graph. It's being shown in this graph. Okay, so what it says that CUSUM is able to detect small shift. Okay, small shift. What do we mean by small shift? Normally, when we say small shift, we are referring to 1.5 and below, 1.5 sigma and below. As we know that in normal control chart, we have 3 sigma above, 3 sigma at the bottom. Okay, so when we say it is small shift, we are normally referring to a shift which is half of this, okay, 1.5. 1.5, which is not able to be detected by rule number 1 of the runs rule, because it is still most likely still within control limit. Okay, the control limit cannot detect this. Okay, so the small shift can be detected, okay, by CUSUM. Okay, that's the good thing about it. Okay, so these are the formula, okay, that I've shown. Okay, the cumulative to get the cumulative value. So there are some there are variation of this. CUSUM plot. We can have a tabular, or we call it algorithmic CUSUM. Okay, or we can have VMAS form of CUSUM. Okay, so um, okay, so the tabular CUSUM, yeah, there's like what we call it, modification of what we have seen earlier, but the basis is there. We have tabular CUSUM, okay, tabular CUSUM, which is dividing this C value, the cumulative value, into C plus. Okay, we have C plus, and we have C minus, cumulative sum of the plus side, the upper side, and the bottom side. Okay, and then you will take the value, the maximum value between this, between 0 or x minus mu plus k plus the cumulative values. Okay, you see here there is a slight modification in terms of the formula here. You have not only having the C plus C values, but also you are referring to, okay, the K values. Okay, K values is inside here. And also it is assuming the starting value of C plus and C minus is 0. Okay, we need to understand what is K values. Okay, the good thing about CUSUM is you can set these K values, what we call it reference value, or allowances of the slack values. Okay, normally, yeah, K can be half of the magnitude of the shift that you are interested to detect. For example, you are interested to detect shift of 1 sigma, so the K value will be half of that. Okay, like in this case, the mean of original minus the mean of shifting minus the mean of original divided by 2. So depend on your interest to detect. If you interest to detect a small shift, for example, shifting of 1 sigma, so the K value going to be 0.5. If you are interested to detect the shift of 1.5 sigma, the K value will be 0.75. Okay, so we can set what is the sensitivity of the CUSUM chart. So this is one of the properties that are very useful in using CUSUM chart. Okay, so the C plus and C minus will be accumulated deviation from the target. Okay, so we see here the C plus and C minus is cumulative. Okay, which is the target is mu naught, okay, which are greater than K. Okay, both quantity will be reset to 0 on becoming negative. Okay, if either C plus or C minus exceed the decision interval, okay, we use H as decision interval. Remember, we have K, we have H, CUSUM chart. Okay, so H is what we call it decision interval. This is like control limit. Okay, this is like control limit in a regular control chart. So this is like a control. Also, we can decide what is the control limit to use. Okay. Okay, let's see the example that will be more clearer here. Okay, if you see here, okay, just look at this example explanation first. Okay, I think there's a break time, right? I think I'll give you a break first, okay, before we continue. Is it okay? Okay, can we have 10-minute break? Yeah, okay, yes. Okay, 10-minute breaks, and I come back to continue with explanation of CUSUM. Okay, shall we continue? Okay, we can continue now. Right. Tabula CUSUM. So that's where we stop just now. Okay. You see that in this tabula CUSUM, okay, we have, okay, let me show the chart first. The chart that we produce with this tabula CUSUM. Okay, I mentioned about the H values. Okay, in designing of CUSUM, we have this H, okay, which we call it decision, where we make the decision based on the H values. Okay, the H can be, we have a small h multiplied by sigma of the process. Same also k, k, we can have a small k, okay, multiplied by sigma. Okay, this value actually can be obtained from the table. Okay, recommended values based on ARL, okay, for particular CUSUM. For example, you are targeting to have k of 1/2. Okay, so if we have k equal to k sigma, okay, meaning that here k is 1/2. In this case, k is 1/2, meaning 0.5 sigma. So in this case, this CUSUM chart is able to, we are targeting the chart to detect 1 sigma shift. Remember that the guideline given that, okay, if this k value is k is half of the what we interested to detect. So this chart, okay, this table is prepared, okay, is by Hawking, okay, researcher by the name of Hawking, give a table of k values and corresponding h value that will achieve ARL node 370. Okay, previously I explained to you what is ARL. ARL is average run length. Okay, so ARL, we can have ARL 0 or ARL node or ARL 1. Okay, maybe I want to check your understanding. You still remember or not? What is ARL? ARL node. Okay, can you put it in chat box? What is ARL node? And what is ARL1? Can you respond to your chat box, please? What is ARL1 and ARL node? Okay, Muhammad apa ni? Hakimi. Okay, ARL1, ARL0 is average run length for stable process. Okay, very good. Okay, Muhammad Fitri also say. Okay, for stable process is ARL0. ARL1 is for unstable. Okay, so when we say ARL0 is for stable process, when we have 370, bermaksud, the meaning is the process is running and we will get false alarm. The first false alarm on average is after 370 unit has been produced. Okay, we are producing, let's say, continuously. The production is stable, no problem with process. Process should be okay. But the first time we will get the false alarm is after we producing, okay, at 370. This is average value. Remember, this is average value. So when we run this in the process. Maybe you get it, the first false alarm is at 100. The second one may be at 500. The third one will be at 400. But when you take the average, you're going to get 370. The first time the first alarm happened. The perfect process will never have false alarm. It will continuously running without triggering any alarm. But as we know that statistics is taken from sampling, okay, it will create some mistakes there. Okay, so ARL1 is when the process is unstable. We want it ARL1 to be as small as possible. So if we get a big shift, we want it immediately after the shift happen, our control chart should be able to detect. But if we see earlier, okay, we see it earlier, it's not detectable, especially even the CUSUM, it takes some time. Okay, from the plot that we have here, okay, we have here, if we have this is the plot, but where is the H value? So we need to decide where is the H value, which is like a control limit that we are able to detect the false alarm. So we see what we have here is a cumulative deviation. Okay, cumulative deviation. So where is the limit that you want to say that, okay, for example, you may put it a limit here as control limit. Okay, maybe you put the limit there. So this is where the H value is important, where you put the H value. Okay, let's say I'm assuming I put it here, the H value. Okay, and also the H value is will be here. Okay, so it takes how many points? Okay, so it will detect that shifting has happened here. Okay, this one is maybe not detectable, but it's still at 0. This is shifting happen, and this is the second shift. So in this one, you get ARL1. This process start to create a problem starting from this point. Okay, starting from this point, you see that create that. So in this case, the second point, okay, you are able to detect it is unstable. Actually, this already unstable, but cannot detect. Why? Because your H value is here. If you put H is higher value, okay, it will take longer time to detect. A longer time to detect that a point is a process is out of control. But if we look at short chart, even the last point at 30 still cannot detect. But in here, you can detect depending on where you put your H value. Okay, so the bigger H value, it will take a longer time to detect any unstable process. So remember that for ARL 0, we wanted the ARL 0 to be as large as possible. Okay, the concept is ARL for stable process. We want it as big as possible. Okay, but the what we call it D factor value, we call D factor value is 370 for short control chart. D factor value is 370, meaning that 370 on average, only then one false alarm that you can detect. Okay, 370. So if ARL1, meaning that when you are able to, how quick you are able to detect when there is process become unstable. We want it as quick as possible. Okay. So meaning that we want it 1, but not always able to achieve that. Okay, we want it as quick as possible. Because the longer we delay the detection, okay, the loss is getting bigger. So when we select a control chart, okay, these are the criteria that we need to consider. Which type of chart that is able to detect as quick as possible. Okay, and as long as possible when process is unstable, because we don't want false alarm. So, but when it is becoming unstable, we want it as quick as possible. When the process is stable, we do not want false alarm. So this is related to decision of using H and K. So this author or the researcher have done a thorough research and provide this table for us to use. So it says that if you are interested to detect shift of, this is shift unstable, there is no shift. They recommend that, not recommend, actually this is the result. ARL performance of tabula CUSUM where K equal to half and H equal to 4. Okay, equal 4 and 5. So there is, if we put it H, it is 4, this is what you get. When the H is bigger, of course, it will take longer time to create false alarm, like I have shown just now. Okay, so in fact, in this chart, bigger than 370, they got it 465. Okay, so it means that CUSUM is better compared to Schwartz control chart because it's not giving false alarm faster than Schwartz control chart. But when there is a shift, okay, there is a shift, let's say a shift of 1 sigma, which is the H, oh, sorry, the shift is 0.5. Okay, so at H5, after 36, okay, after 36 point, only then it can detect. But for 1 sigma shift, okay, it is faster, okay, 10.4. You see, the bigger the shift, it is faster it can be detected. Okay? Let's say the shift of 2 can be detected after 4 points. Okay? So a shift of 3 sigma after 2.5 points. Okay? So this is, we can say that how quick it can detect of, or we can say this is ARL1, okay, because it's unstable. Okay. So let me erase this to make it clearer. Okay, so the value here is ARL, ARL. Same also here, this ARL performance. So when there is a stable process, this only this one, which is no shift. Okay, shift is 0. So this is actually the value of ARL 0. Okay, so the decision of what are value of H and H will play a role, and also what are sensitivity you would like to detect also influence the value of ARL. Okay, looking at another guideline given by the researcher, okay, from Hawking. Hawking, he has done research offering different combination of value H and K. Okay, remember these values are used in the CUSUM control chart where you want to set the decision limit. Okay, so if you want to target performance as good as Schwartz control chart, which is ARL node 3.70, is suggested if you want to use K equals 0.25, use H at 8.01. If you are interested to detect 0.5, you can use 4.77. This one is recommended. Okay, if you are interested to detect shift of 1, you can detect 2.52. Okay, so combination already done in his study. So we just select what value to choose. Okay, in our case, in this example, here we are interested to, okay, so what is shown here is H equal to 5, okay, in this example. Okay, remember this example given earlier? In this example, okay, of producing these values, okay, so where we have C plus and C minus, C plus and C minus. So what we have here is plotted that value of C. Okay, so we have this value. Actually, this point plotted here. This is the raw data. In the raw data, not the CUSUM data. CUSUM data is the one in the bar chart, in the bar. Okay, in the bar. Okay, this is the raw data. If you see the raw data, if we connect this of short control chart, it doesn't show anything. It doesn't show the process is having problem. You see here, it doesn't show the process is having problem. So this is the danger. Okay. Even here, after the shifting, still showing the in control. But when we change this to tabula CUSUM, okay, the CUSUM is showing this value, this bar value. Okay, this value. This value. So up to this point, you don't see anything because it's up and down. But after it is having a problem, the cumulative is keep increasing. Keep increasing the cumulative. Okay, so it will hit this value of h equal to 5. So at this point, it will trigger that the process has to stop. Okay, the process has to stop. And you can see that how quick it is detect. So the starting is from here, you know. This one, this 2, 3, 4, 5, only the 6. Okay, so in this case, ARL 1 here, okay, at the 6 point already can detect. So you need 6 point in order to tell that the process is having problem. Okay, as I say that ARL1 should be as quick as possible, but in this case, okay, it takes until 6 point because why? Because we have h equal to 5. If we make it h is lower, okay, you will be able to detect it faster. You will detect faster. So again, what is the h value to select? Depend on this, where you want to have your sensitivity. Okay, where you want to have your sensitivity. Okay. In this case, given the common value, which is 4 or 5. But here you have more choice, more choice. The h value. You can have the h value somewhere 4 here, okay, or 3. The problem is when you have a smaller value h, you will have maybe tendency to have false alarm as well. Okay, so we need to strike a balance between having effective control chart and having unnecessary false alarm. Okay, that is selection of h and k values. Okay, so let me finish this on this table, tabula CUSUM here. Okay, so in this tabula CUSUM, we need to understand how we get these values. So I think this is already similar as what we have seen. Okay, this value, this one also. Now xi minus 10 minus 10.5. Okay, why 10 minus 5, not 10? Earlier we say it was 10. This is because we have adjusted here. You see here, in this process, our target is 10. Okay, subgroup size is 1. Okay, we are taking only individual values. Standard deviation for the process is 1. Okay, remember standard deviation we use is standard deviation when process is stable. Don't use standard deviation when process is unstable for control charting for the purpose of monitoring. So suppose the magnitude of shift we are interested in detecting is 1 sigma. Okay, we are interested to detect 1 sigma. Because in CUSUM we can decide what sensitivity you want. You want to detect 1 sigma or 2 sigma. Of course, it should be not more than 3 sigma because there is no point of using CUSUM. Because CUSUM is can detect small shift. So I recommend that try to detect maybe 1.5 and below. Okay, because that is where the power of CUSUM is able to detect small shift. If you want to detect 3 sigma or 2 sigma, just use normal CUSUM, normal short control chart, X bar chart. So therefore, okay, out of control values of the process mean, okay, see here, 10 plus 1. Okay, this will be out of control value. The 11 will be meaning that if you got 11, it will be out of control. Why? Because we are already set. We want to detect sigma equal to 1, the shift of sigma equal to 1. So if you got 11, consider out of control, out of control. Okay. So here is like, for example, you have 10. If you have plus minus 3 sigma in regular control chart, the range that you are monitoring is between, okay, 10 plus, if sigma is equal to 1, meaning that plus minus 3 lah. So between 7 to 13. So it's very, very big. Okay. The range is very big. So not so good lah. But in this case, okay, it says that we are only interested on 1 sigma. Okay, 1 sigma here. So it means that okay, you are looking at between 9 to 11. 9 to 11. Okay, a smaller range. A smaller range. So this is what has been decided in designing this control chart. Okay, so we will use a tabula CUSUM, which is k equal to half. Why k to half? Because if shift is 1 sigma, okay, k will be half. Okay, that is the theory. Says that. Okay, we need to, if you want to detect 1 sigma, k will equal to half. If you want to detect 2 sigma, k will be equal to 1. So now, because of that, we have here 10.5, so not 10. So looking into the formula here, okay, you see the formula here. See the formula here. C plus x minus this mu is 10. Remember? Okay, because we want to detect 1 sigma shift, so going to be k equal to 0.5. Okay, so that's why you have the value here is 10.5. 10.5. Okay, this is what we got in this table, 10.5. Okay, and then we need to calculate the C plus. Okay, you have two-sided here. You have the upper side. This is the upper side, which is A, and this is the lower side. Because tabula CUSUM have two-sided. Two-sided. This is what we see in this chart. Okay, we see in this chart two-sided. Okay, on this chart, you can see two-sided. This is C plus. Okay, this is the 0 in the center line there. Oops. Okay, and then you have this C minus here. Okay, C minus. So C plus and C minus. That's why this is we have two-sided tabula CUSUM. H is determined here. Okay, H is there. So this is same as when we connect the point. It's the same thing. This is manual chart. The A was manual using the bar charts now. This is what is produced by Minitab. Okay, you have the upper CUSUM or lower CUSUM, they call it. It's same thing. Okay, so this is basically same as this is C plus. On this side is C minus. Okay, you have the same point, up and down, up and down. Okay, so because of the formula saying that you need to select a value, okay, a value between 0, this one, maximum. C plus is taking the maximum value. Either is 0 or these values. If you get negative, it will reset to 0 here. The bottom part, you have C minus. Okay, C minus. So the maximum value between 0 or another values. Okay, so if it is negative, it becomes zero here. Okay, because we are taking the maximum value. Is it maximum? Let me check. I think we are taking the like this one. Becomes zero when it's negative. Yes, it's correct. And this one, yes, it's taking the maximum value. It's correct. Okay. When it's negative, it becomes zero. So this formula is correct. Okay, both are taking the maximum values. Okay, either zero or any other values. Okay, which is maybe negative values. Okay, if negative, it will reset to zero. Okay, same thing also here. Okay, you will take the bigger value compared to zero. So this is where C plus and C minus of this, okay, two parts of the CUSUM. You have the upper part and the lower part. So these values, and then get the C plus, and then this is the counter. Okay, the counter of the values. So you have 0, 0, 0. So the n counter for n plus is still 0. But this is the first point that it is above the center line, so the count is 1. And then again, the number keep increasing. Okay, second point, third point. So n is just a counter. So it's 4 point, and the fifth point. And then because this one becomes 0, sorry, become negative. So C plus is reset to 0 again. So the counter become again as 0. So see here, number 9, point number 9. See on this graph. Okay. See on this graph, number 9 here. So the C plus becomes 0. But on the other side, this one here has a value. Okay, on this side, 0, 0, 0. Here on the C plus. But on the C minus have a value. So this is what this formula is showing. Okay, you have 0, 0, 0 here. 0, 0, 0, the first. And when you look at the lower side, okay, you have these values. Okay, the counter become 3. But when the value of the lower was negative, it reset to 0. Okay, it can reset to 0. So this is done by this formula. Right? As a result of this tabula CUSUM, this formula. Okay, so this value is resetting to 0 or the actual value. Okay, take the maximum value. So that is the mechanism to calculate that. Okay, and this is what we have in the CUSUM. Okay, in the CUSUM. Okay, another type of CUSUM, we call it mask. Okay, mask procedure. Okay, this is where we have C. I think this one we don't have to. Normally, I don't cover this part. You just be aware that there is a mask procedure for CUSUM. Okay, the use of tabular CUSUM is the mask control scheme. Okay, so instead of using tabula, they have a VMAS, they call it. Okay, VMAS procedure. So the shape of the control chart of VMAS is like this. Okay, shape is V. So this part I don't cover for this course. Okay, you're just aware that there are variation of CUSUM chart. Okay, I would rather go on EWMA, which is in fact the EWMA is more powerful. I mean more convenient to use and also effective compared to. We see that CUSUM is a bit you know the calculation sometimes is can be confusing to us. Okay, so another chart that is more sensitive than short is we call it EWMA chart, exponentially weighted moving average, or sometimes people call it EWMA. Okay, EWMA control chart. Okay, so as same as in the CUSUM, EWMA typically used with individual observation. Okay, again when n equal to 1. As I said, this is going to be more popular because of automation. We are taking 100% inspection, for example, so EWMA can be used. Okay, because the issue of normality is not as serious as when we use short control chart. Short control chart very sensitive to normality assumption. So we will discuss this case, okay, when we will also give a result for the rational subgroup. So meaning that this also can be used when n is more than 1. And also can be used. Also, same also CUSUM also can be used. When n is greater than 1. Okay, but the good thing here is, okay, it is powerful for n equal to 1. But if you have n equal to more than 1, also can be used. Okay, the formula for this, before that, yeah, this EWMA is introduced by Robert. Okay, we know that X bar chart was introduced by Stewart. Okay, Robert was the one who introduced this exponential weighted moving average. So the formula is based on this one. Zi equal to lambda xi plus 1 minus lambda zi minus 1. Okay, so we assume that for the starting values, the z naught or z0 equal to mu, which is the center point, the center line. Okay, so okay, the special thing about EWMA is it has geometric moving average. Okay, geometric moving average. EWMA is sometimes called as geometric moving average. Okay, so EWMA is used extensively in time series modeling and in forecasting. Okay, so it's not only for control chart process monitoring, but also for forecasting. Forecasting for what? Forecasting for example, you want to forecast the demand of customer demand for a certain product. We can use this method as well. For example, you are in your business selling foods. You want to forecast how much will be the demand for certain type of food that you are selling. You can use this method to make forecasting so that you can prepare the quantity that you need to produce so that you will minimize the gap between the demand and supply. Okay, this is the formula. Okay, this is the formula for EWMA control chart. Okay, so you see that it looks like there is some similarity in terms of general format or short. It also has mean. So it has a mean here. It also have L. L is like Z, we used before Z, which is showing the control limit. So L, we can use L equal to 3, for example, 3 sigma L. L is just a value, a constant, and sigma. Okay, and then we have here lambda divided by 2 minus lambda. And this term, okay, 1 minus 1 lambda to I, okay, will be disappear as the number of I increasing. Okay, so when 1 minus 1 minus lambda to I, when I is getting big, so this term will be dropped. Okay, this term 1 minus, so this one will be dropped when the sample size is getting bigger. So this is what is shown here. In the steady state, then the formula just become like this. Okay, so it's simpler than CUSUM formula. So when you see here, okay, let me show, yeah, the shape. This is the shape of EWMA. EWMA. So at the beginning, it looks very complex, especially this part, this part of the curve, because the control limit here keep changing. They keep changing the values. They keep changing. But after it stabilizes, okay, it becomes just a straight line. Just become a straight line here. It becomes a straight line like this. Okay, no more changes. Okay, so these changes is due to this formula. If you see this formula here, okay, this formula, the one that I crossed just now, okay. So as the I value is getting bigger, you see this I value here to I, okay. So 1 minus this also become big. No, is approaching to 0. Okay, approaching to 0. This term becomes 0. 1 minus lambda. Okay, so you just left with 1 minus 0. Okay, 1 minus 0. So that's why this term, as the I is increasing, the formula just become like this. Okay, so if you look at the example, this example is showing the same values that we have used for CUSUM. Same values, 9.45, 7.99, 9.7, using the same values. And calculating the ZI, okay, how do you get the ZI? The ZI is from this formula. Okay, from this formula. ZI, Z1 equal to lambda. So now we need to decide what is the lambda value to use. Okay, in CUSUM we decide H and K, but now the lambda. The lambda is sometimes known as smoothing constant. We call it smoothing factor. Smoothing constant is a constant. And the value of lambda can be between 0 to 1. Okay, of course, we don't use 0. We use 0.1, 0.2, 0.3, up to 1. Okay, because in this value, you have lambda here, you have 1 minus lambda. So if you have lambda equal to 0.1, on this side, going to be 0.9. What it shows here is, okay, lambda xi, meaning that the current value, okay, the current value. 1 minus lambda, zi minus 1, this is the old value. Okay, then the current value plus the adjusted old values will give you the current z. Okay, so this formula is showing the influence of historical values. Okay, previous data. Okay, previous data play a role in the decision making for the process. Okay, this is the current. Okay, because xi, this is the current value. So how much you want the influence of the old value, that depend on alpha. So if you give alpha equals 0.1, meaning that the new value has 0.1 influence, but the old value will have a big influence because it's going to be 1 minus 0.1, which is 0.9. So it shows that the old value is very important. Yeah, old value is very important. So this is what we put it in this formula. So okay, as a recommendation, sometimes people use the value of lambda 0.2. Okay, And with a bigger value of alpha shows that the the the, the current observation value is important, but it's low alpha, sorry, low lambda is showing that the old values is more important. Okay, so okay, let's see this example. Okay, in this example, lambda is given, okay, 0.01. L also given, 2.7. Okay, so where is the L? L is used in this formula. Okay, this is L. Okay, this is L here. So we know the mean. Okay, we know the mean of the process. Mu naught. L is given 2.7 just now. So this is the coming from a stable process also, the sigma square root. Lambda is given 0.1 just now. So this is straightforward, not difficult to use this. So you just calculate the Z. Okay, the Z is coming from, as I say, this Z value is coming from lambda x I. What is I? I is depend on this. Okay, subgroup number 1 is I equal to 1. Okay, plus just opposite of this one, meaning that 1 minus lambda. If you have here is 0.1, here going to be 0.9. And multiply by the old Z, the previous Z. Okay, the previous Z, which is Z. For the beginning, it will be Z0 lah. Okay, for example, here is Z1, go to this. Okay, when you have Z2, this one becomes Z1. Then keep continuing calculating this until you have all the values, and then just plot. Okay, one thing that that was the plotting. That what you plot is EWMA values. Okay, which is in this case is represented by Z. Okay, represented by Z. Okay, but to decide the control limit, we use this formula. Okay, this is the formula. When the process stable, you use this one. Before you get the stability, you need to start with this one. Okay, even these values, this one can be used for the whole chart, but when the I become big peak, this value is not significant because it's going to become 1. So only remaining this one. So if you want to get this value here, this part, the blue color, okay, this blue color is actually determined by this formula, which is mu plus L sigma square root of, here you have lambda, here you have lambda divided by 2 minus lambda. 2 minus lambda. It's very simple, but it is powerful. This method is very powerful. So this is sigma. Sorry, mu. The mu is here, the center is here. Okay, L is given, lambda is given. The only difficulty is somewhere here, where you have to have more calculation at the beginning. One is stable, we can like that. Okay, so I think this example also quite clear there. Okay, okay. So I think that's all for today. Any question? This table provide you guideline, okay, how to select the L and lambda. Okay, what if you select, for example, lambda, the lambda equal to 0.1, so the L will be this one. Okay, so this is recommended by researchers from Lucas and Sakuchi, they have done a lot of experiment on this. Okay, average run length for several WA control chart scheme. Okay, so depend on the what shift that you would like to detect. Okay, for stable, you see, for stable process, they even get very impressive ARL values. Okay, ARL values is 500. Should only give 370. Okay, so this is meaning that stable process. So it ran longer compared to short. Okay, on average, after 500 runs, only then false alarm happen. Okay, compared to short, it is 370. Okay, it gives you 300. So meaning that this is very good method of process monitoring. But when there is a shift, okay, this is basically for unstable process lah, because there is a shift here, shift 0.25, 0.5, and so on. Please read also this, this your ebooks. This is a very, I think very useful information that we have here. Okay, I will identify a few questions for you to do the exercise. Okay, so is there any question before we stop for today? Any question? You can put in chat box or you can switch on your mic. Okay, if no, yeah, I think that's all for today. Thank you very much. And please check your Telegram. I will give a few examples for you to do the exercise. Okay, Assalamualaikum warahmatullahi wabarakatuh.